sunset. So plan for that. It's an amazing location. So bring a picnic and arrive even earlier if you would like. But we have to start cracking down on late arrivals, unfortunately. So, but that's it.
Okay, I'm going to introduce the next 2 months speakers briefly, and then I'll introduce our wonderful speaker tonight. We always meet on third Wednesdays of each month. So May 18th, we have Bruce McIntosh, Stanford, Deputy Director of KIPAC, which is the Kavli Institute for Particle Astrophysics and Cosmology. He's speaking about imaging extrasolar planets. In the past 27 years, more than 5,000 planets beyond our solar system have been discovered, and that number was just raised in the last few days. However, we still don't know if our solar system is rare or unique, and many systems are very different from ours. We'll learn more about the technology that discovered these extrasolar planets, as well as future planet hunting telescopes. The ultimate goal is finding a second pale blue dot, an Earth twin with possible biosignatures of life. That's May 18th. And on June 15th, Cynthia Yu, Department of Physics, Stanford, is speaking about measuring the beginning of time from the bottom of the world. Measurements of the afterglow of the Big Bang, the cosmic microwave background, have allowed physicists to piece together much of our understanding of the origin, composition, and evolution of the universe. Cynthia Yu works on building new tools to study the astroparticle universe. She has experiments using the South Polar Observatory, Simon's Observatory, and the CMB-S4 Observatory. These house the experiments to assist us learning more about the cosmic microwave background. Tonight, Dr. Pascal Lee will be speaking with us. He's a senior planetary scientist at the SETI Institute, chairman of the Mars Institute, and director of the NASA Houghton Mars Project in the US Space Agency's leading planetary analog field research project in the Arctic. He's based at NASA Ames. He holds a ME in geology and geophysics from the University of Paris and a PhD in astronomy and space sciences from Cornell University. He was Joseph Viverka's last graduate student and Carl Sagan's last TA. His research focuses on the possibility of extraterrestrial life on other planets, in particular through studies of water and ice on Mars and planning the future explorations of Mars and beyond. He's led over 30 expeditions to the Arctic and Antarctica for planetary analog studies, including a 402-day winter over in Antarctica. He's a recipient of the US Antarctic Service Medal. He also does research on the search for extraterrestrial intelligence, or SETI. He first argued, based on the late evolutionary appearance of technology on Earth, that the number N of advanced civilizations in any galaxy is likely to be a very small number. He's also a certified helicopter commercial pilot and flight instructor. And he's an artist, member of the International Association of Astronomical Artists. His paintings about space and time and our tiny yet hopeful place in their vastness are in collections worldwide. He also works in the service of his dog, Apollo, one of the surest signs there's intelligence on Earth. Pascal will now speak to us on N-1, Alone in the Milky Way, and we welcome Dr. Lee tonight. Thank you so much.
Thank you so much for having me. Thank you, Linda, for this introduction. It's a real privilege for me to be with you tonight. And let me immediately jump in to say that I have no idea how many civilizations there are in our galaxy, let alone in others. But the approach I took to get to n approximately equals 1 is by trying to be really pragmatic about the data that we actually have in hand, even if it comes down to the one example that we have of the Earth, and to extrapolate and speculate as little as possible in order to estimate the different terms of the Drake equation. And I'll get into all this tonight. I'm giving myself about an hour or so it won't last longer than it might seem. But let me just jump straight in and tell you this, tell you the story of where we stand, I think, in our estimation of the number of intelligent civilizations in our galaxy. So I'm going to share screen here. There we go. First of all, let me say from the get-go that although I'm affiliated with the SETI Institute, the Mars Institute, two nonprofits, and NASA Ames, what I'm going to say tonight is not endorsed by these agencies, and so they can relax and not be worried about what I'm going to say. It's also not necessarily endorsed by the San Francisco Amateur Astronomers either, but hopefully I will find some kindred spirits tonight. So this is, of course, the Andromeda Galaxy, and I'm showing it because it allows us to have a sense of what our own galaxy might look like if we could take this step back and look at our own Milky Way galaxy. But the Andromeda Galaxy and the Milky Way are relatively similar, so I think this is a good stand-in. Our own galaxy has approximately 100 billion stars, although there are some estimates that think that if you count the really dark objects, that we might be up to 400 billion stars in our galaxy. And our galaxy, of course, is about 100,000 light years across. And we, of course, are neither in the center of our galaxy nor at the far edge, but somewhere in the middle, halfway out from the center in a spiral arm of the galaxy. Now, we tend to think of other civilizations in our galaxy in terms of a sort of a Star Trekian or Star Warsian universe. You know, we just haven't joined that galactic club yet, but somehow there must be civilizations out there. And, you know, those who are in on it hang out in bars across the galaxy. We just haven't been invited yet, or don't know how to get there. And this is, of course, deeply rooted in our culture. Even among my colleagues and people that I often talk to, there's a sense that unless you are open to the idea that there are many civilizations out there, you are somehow closed-minded. And what I would like to convey tonight is that you can be very open-minded and yet come to a pragmatic conclusion that we might still be, you know, very lonely here, because it's not clear at all that there are these civilizations that are, you know, that our galaxy is teeming with these civilizations. So let's quickly estimate the number of planets in our universe. Well, we have about 100 billion galaxies in our known universe. There are approximately 100 billion stars per galaxy, so that's another 10 to the 11. And let's say that the number of planets or planetary bodies per star is approximately 10 on average. And, you know, in our own solar system, we have far more than 10 planetary bodies, but some systems might have none. So I think 10 is not totally unreasonable. The number of planets in our galaxy, just our galaxy for now, would therefore be 10 to the power 11 times 10, that's 10 to the 12. That's 1 trillion planets in our galaxy alone. Now, this is a staggering number, although when you think about it, it's still 30 times less than the national debt, which just this past February reached $30 trillion. But nevertheless, 1 trillion planets in our galaxy, that's a healthy number. In terms of the planets in our universe, well, you multiply that by another 100 billion galaxies, and you get to this amazing number, which is 100 sextillion. It's a 1 followed by 23 zeros. And that is not even going to impress chemists, because that's almost a mole, but not quite. Okay, so if you're familiar with Avogadro's number in chemistry, 1 mole is about 6.07, 10 to the 23 atoms. And so here you are, that's roughly the number of planets in our known universe, about a mole. Now, the Drake equation is a formula that is mathematically very simple. It's a multiplication of 7 terms. And the formula is supposed to give you the number of advanced civilizations in our galaxy, or in any galaxy. And that would be equal to the following terms multiplied by each other, because these are factors that essentially come into play when you're trying to estimate the number of advanced civilizations in your galaxy. You start with the rate of star formation. That's the number of stars that form on average per year in your galaxy. The bigger galaxy will have more stars forming per year, the smaller ones. So this rate of star formation has embedded in it the size of your galaxy in some sense, times the fraction of stars with planets, times the number within each planetary system where there are the number of environments that are suitable for life in each one of these planetary systems. So the definition of that is that if you have a planetary environment that allows liquid water to be sustainably present over the long term, then you have a planet that is suitable for life. It's a bit simplistic, but it's a useful, helpful definition. It encompasses temperature, pressure, and sort of a thermodynamic range of conditions that life as we know it enjoys. Times the fraction of planets that are suitable for life where life actually appears and is present. So that's F sub L. Times the fraction of those planets with life where life is able to become intelligent. Times the fraction of those planets with intelligent life that actually become an advanced civilization. So there's a distinction here between just being intelligent and becoming an advanced civilization, and we'll see why there in a bit. Times finally the term L, the capital L, which is the average longevity of an advanced civilization in our galaxy. Now, we don't actually know the exact number of any one of these terms, but some of them we know relatively well within an order of magnitude, whereas other terms we still don't know very well at all, and are off by 2-3 orders of magnitude. I want to point out that mathematically, all these terms that have an F in them, the fraction of stars, planets, the fraction of planets that are suitable for life that actually have life, the fraction of planets with life where it becomes intelligent, and the F sub C, all of these F terms are less than 1, less or equal to 1. So it's a number between 0 and 1. If all stars had planets, which is what we are finding now and are so enthralled about, we're finding exoplanets around so many stars. Even if all stars had planets, F sub P would just be 1. It doesn't really pump up your number N very much. On the other hand, any one of these terms, if it were close to 0, any one of these F terms, okay, if it were close to 0, it could bring down the whole number N. So the fact that we're discovering lots of exoplanets right now is very good, of course. It means that F sub P is not going to be the term that will kill you in the Drake equation. But it doesn't necessarily mean that N won't be reduced to a very small number if any one of these other Fs, F sub L, F sub I, or F sub C were a small number, anything close to 0. So for N to be a large number, none of these F terms, in fact, none of these terms in total, is allowed to be a small number, anything close to 0. Okay, so let's explore the values that we commonly give to these terms. In the optimistic scenario, R is 50. The other terms are all maxed out at 1. N sub E at 1 means that we think that in this optimistic scenario that every planetary system has at least one environment that's suitable for life, meaning where there's liquid water. And the capital L is that, well, we think that an advanced civilization can live to about 1 million years on average. Okay, well, if that were true, then N is 50 million advanced civilizations in our galaxy, which means that the nearest one is about 10 light years away. Now, that's the optimistic scenario. At the SETI Institute and in common discussions of SETI, our star is usually 20, the other terms at 1. The longevity of a civilization is 5,000 years. And that's neither very optimistic nor pessimistic. It's just historically based. It's how long we've been. If you consider us to be a continuum since ancient Egypt, so to speak, we've been around for 5,000 years as a sort of a global civilization expanding slowly. Then the number N is 10,000. There would be 10,000 advanced civilizations in our galaxy right now. And that would mean that the nearest one might be no closer than about 1,000 light years. which incidentally makes communicating with them automatically very difficult unless we were really lucky to have one nearby. All right, I'll show you tonight what values each one of these terms has according to my pragmatic approach to using only data that we sort of have in hand. And there is something called the Fermi Paradox that pervades all this. And the Fermi Paradox can be summarized this way. Enrico Fermi, of course, won the Nobel Prize, was one of the discoverers of the neutrino. He said that, well, if the N number is large, where's everybody? How come we don't see evidence of these advanced civilizations coming to the Earth, landing here? And of course, I'm dismissing right now all the UFO identification, so to speak, that attribute UFOs to advanced civilizations visiting us. What the Fermi Paradox says essentially is that if N is a large number, how come we don't see more evidence of these advanced civilizations in our galaxy? And there's a long list of, quote, explanations or excuses. Okay, N is large, but it just appears small is sort of the gist of every explanation. And so one explanation is that interstellar communications and travel are too difficult. So it's not worth pursuing, therefore nobody visits us, and that's why we feel alone. Or intelligent civilizations ICs are too alien. So they are communicating with us, but we just don't understand what they're saying. It's lost in translation. We can't make it out from the noise of the cosmic background. Or intelligent civilizations are too advanced or busy. We mean nothing to them. They have other fish to fry. Or they're not radio loud for long enough. They've all switched to cable. So in other words, they are actually there. It's just that they use technology that would go under the radar, so to speak, for us. And so they are not detected. They are avoiding us. And Carl Sagan famously said that the best proof that there is intelligent life in the universe is that they haven't tried to contact us. Okay, so that's the best proof that they're intelligent. Maybe they are breeding us. Okay, we're someone's ant colony, and so of course we can't understand or fathom their presence. They are protecting us. They are following the prime directive. So we're just deemed not ready yet for prime time, and so we're just allowed to continue to evolve slowly until one day we'll be ready. They're studying us. We're somebody's science project. They're training us. We're not worthy yet. We're not potty trained, but there's a training crew that's on its way to teach us, how to become a galactic worthy civilization. And so they're on their way. Or intelligent civilizations can't agree on what to do. Okay, and maybe they have a Congress as well. Or they are here, but they are unseen. Okay, so in which case we're in a lot more trouble than we think. Some people think that SETI is just too young. We haven't been looking for long enough, so we've just started. SETI is misguided. Okay, we're not doing the search right. We have assumptions that are incorrect. Somehow, our heart is in the right place, but we're not doing it right technically. And then, of course, SETI is suppressing evidence. They've actually been found. They are there. They are amongst us, whatever. And so I just put this space intentionally left blank. All right, is sort of the interpretation. Well, I can tell you that none of these, of course, are confirmed or established. These are just possible explanations of the Fermi paradox. So what is the rate of star formation today in our galaxy? Well, stars form in stellar nurseries. These are giant clouds of gas and dust that become at some point gravitationally unstable when they're dense enough, and they collapse and they form stars. And so we know roughly by knowing how many star forming regions there are in our galaxy and how many stars come out of each in general, that the rate of star formation in our galaxy is somewhere between 20 and 50 stars per year. This is actually a pretty well constrained number. I'm going to go with about 20 stars per year because everybody will agree that that's a minimum that is happening right now in our galaxy. Okay, and I'll just move on to the next term. The fraction of stars with planets. Okay, this is where the discovery of all these exoplanets comes into play. Well, first of all, we had a theory of how planets form, in fact, several, but one predominant one where planetary disks form, a protoplanetary disk with protoplanets. These are giant disks of molecular gases and dust. And essentially the disk at some point clumps up in different locations, and through gravitational interactions, you have accretion of larger bodies, and over time, planetesimals grow into planets. And just a few weeks ago, the Subaru telescope and Hubble Space Telescope reported this happening in real time, so to speak, visibly, at least in the infrared, near AB Aurigae. So AB Aurigae B, which is shown by the arrow there at the bottom, is supposed to be a planet, a protoplanet now forming around the star, which is actually blackened out here. The other bright blob that you see near the inner part of this system is not necessarily another planet forming. It could be part of the imperfect blocking of the star's light. So the thing that was more confident about interpreting is that the outer protoplanet that we see here, the outer bright blob, is a large protoplanet forming well beyond the orbit of Neptune, by the way, around this particular star. But at least this is now a planetary disk in action. Kepler, of course, looked for exoplanets around the nearest stars within 3,000 light years from us in a particular direction along one of the along the Orion spur, basically, of the Sagittarius arm in our galaxy. And as Linda was, I think it was Linda, somebody was mentioning earlier, we are now at over 5,000 confirmed exoplanets around nearby stars within 3,000 light years. So that's a very promising number, and that tells us that planets are. It can no longer be argued that planets are a rare phenomenon, which wasn't clear to everybody until Kepler's work, mostly the Kepler missions work. Okay. Now I've also come up with this plot, which just shows you the closest star systems to us within 10 light years from the sun, and also the planets that the exoplanets that are now known. Now there's approximately 10 star systems, including the sun, within 10 light years of us here on Earth. And of these, approximately 5 have planetary systems around them, okay, that are sort of known. And Alpha Centauri actually does not have known planets around any one of the larger components A and B, but Proxima Centauri, which may or may not be in orbit around Alpha and B, A and B Alpha Centauri, Proxima Centauri has at this point 3 exoplanets, including one in the so-called habitable zone. It's at 0.05 astronomical units, so very close in, because Proxima Centauri is a red dwarf, so you have to be close in order to still be warm enough to have liquid water at your surface. So this is a close-in planet. It orbits the star in 11.2 days. And it's about 1.17 Earth mass. So it's a little bigger than the Earth. It would be spectacular to go visit this world in the habitable zone of Proxima Centauri. Okay, but other stars beyond, most of which, by the way, are red dwarfs, also have planets. Barnard's star might have 1 exoplanet at 6 light years. Lumen 16 does not have exoplanets that are known. Y08, 55, 07, 14 might be a brown dwarf or rogue planet itself, so it could be in a class of its own. Wolf 359 has 2 known exoplanets. It's also a red dwarf. Lalande 21-185 has 3 exoplanets, although the third one is to be confirmed. Sirius AB, a binary with a very bright blue star, it has no known exoplanets so far. And let me move this here. Louis 10 726-8 has no exoplanets, and Ross 154, no exoplanets known yet. So we have about 10 exoplanets within 10 light years, and 5 systems out of 10 star systems that have planets. Okay, so about a half of them. So this is where I'm going to suggest that we I'm going to suggest that F sub p, the fraction of star systems with planets, is roughly half. It's not all of them. At least we don't have data that supports the claim of all of them. But on the other hand, it's not a small number, and it seems like planets are very common. So I think 0.5 is a number I'm comfortable with. And not only is it consistent with the Kepler exoplanet data, but it's also consistent with what we're seeing within the closest 10 light years from us so far. All right, how many environments are suitable for life within a planetary system? Well, of course, we're familiar with this Goldilocks zone concept, where there is a distance range from your star within which liquid water would be stable at the surface of your planet, because it would be neither too hot nor too cold. And the solar system is shown at the top there, where at a healthy distance from the sun, we have these different planets. Of course, the ranges are not shown to scale, but the idea here is that the Earth, of course, is expected to have liquid water on its surface, and surely it does. Mars and Venus, marginally. However, their surface conditions at the edges of these Goldilocks zones are heavily affected by whether or not you have an atmosphere, a thick one or a thin one, or none at all, etc. So this is why you have different bands here within the Goldilocks zone. Of course, as you get to smaller stars, you need to be closer in order to be within your star's habitable zone. Okay, but this habitable zone concept is very limiting, and I don't think that it is the only factor, of course, that will govern whether or not a planet will have liquid water stably within it or at its surface in the long term. In Mars, for example, we now know that the surface, of course, is a global desert with very little liquid water, but there is actually plenty of water in the form of ice in the ground, and also, of course, at the poles in solid state. And if you go deep enough into the ground, temperatures will rise just like it does in a mine, and at a depth of about 2 to 5 kilometers, depending on where you are, thermal models predict that you will encounter liquid water in the subsurface of Mars. Okay. There are also hot spots on Mars, which we think are still active. The volcanoes of Mars, for example, are so large that they have probably been active in the history of Mars for the bulk of Mars's history for some of them. And they might still be active today. They're not actively erupting, but they might not be dead volcanoes. They could be just dormant. So first of all, it would be a spectacular thing, of course, to see an eruption happen in our lifetimes, but that's not really very likely. On the other hand, we shouldn't think that they're not still warm in their subsurface, very near the surface. And so this, combined with the fact that we've now found a number of caves, including the one I'm showing you here on the right at the bottom, or near the bottom, that's the entrance of either a giant lava tube or a crater pit that is actually bottomless, as far as we can tell. The opening is approximately 150 meters across. Its depth is at least that. And no amount of image enhancement has been able to bring up anything at the bottom of these pits. Some of these lava tube skylights or lava tube entrances show dunes and rocks at their bottom if you do the proper image processing to sort of enhance the part that's in the dark. But this particular one, called the Jeanne Pit on Arsia Mons, is bottomless. And my point about this is that these caves are really extraordinary opportunities, I think, to search for life, because these volcanoes being possibly still active and therefore still releasing heat, these caves could be combining several key factors that life would really enjoy on Mars, life as we know it. A sheltered environment, shielded from galactic cosmic ray, ionizing space radiation in general, micrometeoritic bombardment, stark temperature changes during the day and night. All of this you'd be sheltered from if you were in a cave like this. And on top of that, if you have some warmth and including water vapor being released, water vapor being the most common volatile that's released in volcanic eruptions, you could have a very cozy environment for life to be thriving in on Mars today. So the point here is that there could be liquid water at depth on Mars in abundance. And that's one concept to expand this Goldilocks zone idea. So here's a painting I did illustrating what it might be like at the bottom of the Jeanne pit on Arsia Mons. One day we might need a cable to rappel down, and of course we wouldn't be the first to explore. You'd send robots in there first, but here we are looking at rock glaciers inside this cave. Now, beyond Mars, of course, you have the giant satellites, the satellites of the giant planets. Europa, we know, has an ocean underneath a crust of ice. The ice crust on Europa is about 15 to 25 kilometers in thickness. The ocean depth is 60 to 150 kilometers. And in case you had never quite realized that, I'd like you to sort of ponder that. The Mariana Trench on Earth, the bottom of the sort of the deepest ocean floor on our planet, is at a depth of 11 kilometers. Okay, we're talking on Europa of about an ocean that is 60 to 150 kilometers in depth. So these are, truly abyssal depths, and God knows what is living down there, if anything. So I've speculated here in this painting that you could have a giant beast lurking underneath this rocket that just landed on Europa. It's a painting I call Except Europa, because Arthur C. Clarke in his novel 2010, A Space Odyssey, had warned humanity basically not to land on Europa. Of course, here we're doing it. Anyway, Enceladus is in a similar situation, an icy moon of Saturn, a crust of 10 to 20 kilometers, and then an ocean depth of about 40 kilometers, not quite as deep, but still, way deeper than the Mariana Trench here on Earth. And so that, of course, would be an incredible place to go explore. I want to point out that NASA, the Decadal Survey, which is this document published by the NSF that guides NASA's scientific research, is recommending, among other things, missions to Europa in the decade to come. So, sorry, to Enceladus in particular. So I think that we're going to find out a lot more about these geysers of water and water vapor that you see here at the surface of Enceladus and its ocean and whatever might be lurking underneath in the decade to come here. Of course, you have Titan as well, the largest moon of Saturn, which itself has a very thick atmosphere, 2 bars, 1.4 bars. So, I mean, in other words, it's 40% thicker than the Earth's atmosphere. It's quite incredible for a moon that is actually has a lower gravity than even our own moon. Our moon's gravity is 17% of that of the Earth. Titan's is 14%. So, you could make big hops on Titan. I'm actually working with some students on a design of a spacesuit for Titan, which is really interesting because you don't really need a pressure suit for Titan since you have a thick atmosphere around you. So you would be much more mobile in a suit on Titan. You just need it to be very warm. So that is something we can do. And anyway, it's an interesting problem that I'll share once we have the final design. Giant planets themselves could, in their atmospheres, have environments that are suitable for life. Carl Sagan and Edwin Salpeter at Cornell had speculated that there might be floaters in the atmosphere of Jupiter and possibly Saturn as well. So these would be creatures that would sort of live in this zone that is deep enough in the atmosphere of these giant planets to be protected from space radiation and their magnetic fields. from particles that are high energy particles that are caught in their magnetic fields, and at the same time not so deep that they would be crushed by pressure and temperature, and so sort of almost a marine environment in some sense, but in an atmosphere of this giant planet, with floaters and predators. A whole ecology was sort of imagined. And then finally, to understand the chances of having a habitable planet, it's not just whether it's close to its star or not, or whether or not it has environments at depth that are suitable for life. You also have to consider where that planet is in relation to the center of its galaxy. Galaxies experience gamma ray bursts, which are high energy releases, releases of high energy particles, in particular in gamma rays, when supernovae explode. And galaxies in general have about a few of these gamma ray bursts per million year. Okay, and so of course they're much more frequent because there are more stars near the center of a galaxy than on the outskirts of a galaxy. And gamma ray bursts are really nasty, and they could actually wipe out life on a planet, at least at the very surface of the planet, very quickly. You have to imagine that a gamma ray burst releases within a few seconds as much energy as the total output of the sun throughout its 10 billion years of life. And so these are very powerful events. Life would not survive if exposed to it. And so the thinking is that if you're very close to the center of your galaxy, you're in a very precarious situation here if you want to have life expand at the surface of your planet. The Earth is sort of a healthy distance out. We're still at a probability estimated of 50% of having life on Earth wiped out by gamma ray bursts. And it's conceivable that some of the past mass extinctions that we've experienced on Earth, which are not explained by giant impacts, could be due to gamma ray burst events from nearby supernovae. Of course, it's not established or well understood, but the point here is that it's not just your distance to your star or whether or not you have liquid water at depth that matters. It's also where you're located in relation to the center of the galaxy. Location, location, location. So the number of environments suitable for life in the planetary system, well, I would say that, well, if you look at our own system, you can count maybe even 10 environments, 10 planetary environments that could be suitable for life in our own solar system. I would say that if you go with N about 1, which is on average, if you have a planetary system, there'll be about 1 environment that's suitable for life in each planetary system on average. That's a decent number. It's a bit optimistic. We're claiming here that this is an average number. So it's a bit optimistic, but I'll go with it, given that in our own solar system, we have, at least 10 environments that could be suitable for life, at least in theory. So what fraction of these environments with liquid water in a sustained way actually has life on them? So to understand the probability here, we have to figure out how does life start. And of course, we don't know how life starts and evolves into, from chemistry to being biological. The Urey-Miller experiment was a very important step in our understanding of the chemistry of life, because Harold Urey and Stanley Miller at the University of Chicago were mixing gases that were believed to be common on early Earth: methane, ammonia, water, hydrogen. We now know that it was mostly CO2, in fact, but nevertheless, they had different mixtures that they were experimenting with. If you zap these mixtures of gases with high voltage in a glass jar, and then you condense the products of this reaction, you can collect organic material and analyze it. And in the organic material that was collected and analyzed, they found a plethora of amino acids. Okay, including amino acids that were used by life on Earth, but also a whole host of amino acids that life does not use. And as you probably recall, all our proteins are made of amino acids, and all our proteins in all of life on Earth uses only about the same 23 amino acids. And so not only that, but the left-handed versions of them, not the right-handed one. So the fact that in a glass jar experiment like this, you can produce a wide range of amino acids means that at least to form these very early chemicals at the basis of proteins and life, it's actually relatively easy. Okay. Now, the origin of life is understood to have different milestones. First, you have to synthesize some organic molecules that are going to be at the basis of life. Then you want to get to the stage where you have self-replicating RNA. Then you want the RNA to sort of build a cell wall around itself. And eventually you have a primitive cell with mostly RNA genome, RNA being the ancestor of DNA. And then eventually this stabilizes into something that is based on DNA, but still uses RNA as a sort of a template for protein production. Anyway, the Urey-Miller experiment happened in 1953, so we got that step at least reproduced. It's very rapid. It can be done within the hours of a Urey-Miller experiment. In 2009, the Scripps Institution reported creating immortalized RNA. These were synthesized RNA molecules that were able to self-replicate without the addition of proteins, without any external chemical aid. These RNA strands were able to fight for themselves, reproduce, and get rid of things that were not the same as themselves. And so this was a major step, although it's not quite the appearance, the emergence of RNA directly from amino acids. Of course, we synthesize RNA that were able to reproduce themselves, but it was an important step, I think, in sort of understanding the steps towards the origin of life. But of course, we're still left with steps 3 and 4 that are totally unreproduced, and maybe they will take a lot more time and probably sort of exposure of chemicals. In other words, statistical opportunities to really happen. In any case, it's now understood or believed that the most likely environment where life appeared on Earth is at the bottom of the oceans, of the early oceans of our planet, near hydrothermal vents, in places where you had the right, at least a plausible mixture of nutrients, chemical compounds, temperature, pressure conditions that favored this type of prebiotic and biotic chemistry. Okay. And what we do know from the fossil record is that life appeared very early on Earth. This, I think, is a very important thing to realize. So these are all examples of primitive forms of life on Earth. The three ones on the left are biosignatures in very ancient rocks on Earth. The one on the far right is actually a modern Deinococcus radiodurans. It's a sort of an end product. It's still a cellular, multicellular organism. Actually, it's a unicellular organism. But this particular bacterium has membranes, has 4 sets of its own DNA, which is really unusual. And it's sort of unique in that particular configuration. Which is why, so Deinococcus just means that it's a microbial bug, but radiodurans means that it endures radiation. And the fact that it has 4 identical sets of its own DNA means that if any one of these DNA encoded genetic information is disrupted by radiation, for example, the 3 others will kick in to fix the error. And so this is quadruple redundancy, the way NASA loves it. And life has come up with that on Earth. We don't know exactly why. Deinococcus radiodurans, you would think, is the ultimate space traveler, and in the sense of radiation shielding, it is. but it doesn't fare very well in a low pressure, in zero pressure, in the void. Nor is it very good with very low temperatures, etc. So it's clearly a terrestrial form of life, but at the same time, it has an incredible adaptation here. My point about all this is that cellular life is, unicellular life, early forms of life are very resilient. They will, in other words, life has not abandoned unicellular life just because it has evolved over time. Unicellular life is still pervading life on Earth, and it appeared very early, and it has evolved over time into forms that are still relatively simple, but with some really robust solutions against destruction. And so there's something very powerful about microbial life. A colleague of mine, Charlie Coquelle, wrote a very insightful book called Impossible Extinction, which is that you can wipe out evolved forms of life on the planet, but it's very difficult to get rid of microbes. Okay, very difficult. And so the message here is sort of twofold. Microbial life started very early. Life started very early on Earth, and that is suggesting that it's easy to start life. And the solution that it found for life is a very durable solution. It's a very stable, robust solution to the point where 4.5 billion years later, we're still having around us the same types of microorganisms that existed early in Earth's history. Okay. And so this is shown here. This is a column representing time from 4.6 billion years ago at the bottom when the Earth formed to the present. And you can see that the oldest rocks known on Earth are about 4 billion years in age. And it's roughly as well the earliest record of life on Earth. So we don't actually have life in the very oldest rocks we have found on Earth, but in some that are just barely a bit younger. The point here is that life appeared very early in Earth's history, and it took possibly no time to just a few million years for life to appear. And the fact also that microbes are so robust against extinction means that microbial worlds are probably very common in the universe, in our galaxy, and possibly even in our own solar system. I would not be surprised if we found microbes on Mars, inside Mars, microbes in Europa, microbes inside Enceladus. Okay, microbes are like the ultimate survivors, and they were able to start very early on Earth. It doesn't take very long for life to come up with that. And so therefore, I would submit to you that because life on Earth appeared early, it was easy, microbial worlds are likely common. The fraction of planets where environments are suitable for life, where life actually appears, might be half. I don't want to say one, because that's a little too extreme. We don't have the basis for that. But it doesn't look like, from the one example that we have of the Earth, that it looks like it was something difficult. And so I'll give it a 0.5, somewhere between, halfway basically between 0 and 1. What fraction of planets with life evolves intelligence? So what do we mean by intelligence? You could artificially define intelligence, almost any way. You could call it the beaver, or you could call it the emergence of the giraffe. We define intelligence here by a species that somehow becomes able to transform its environment through technology. Okay, now a beaver transforms its environment through some pretty interesting engineering, but it's all done by instinct. It's not like they have, engineers among them who are discussing the best way to build a dam and they improve on it, sort of from a from a technological standpoint. Okay, Homo erectus, however, was a early human that was able to start creating tools of putting things together that had no reason to be put together, okay, like a rock and a stick to turn into an arrow, okay, to create technology. And so this is our definition here of intelligent life, but you could choose it in some sense in any way that you want, okay? So Homo erectus appeared roughly 1 or 2 million years ago here on Earth, and what characterizes Homo erectus is, again, its ability to use the materials of its environment and turn them into tools and applications that are essentially technological. Okay, so here's Mr. and Mrs. Homo erectus getting very defensive about something. Maybe it's a predator, maybe it's just a tax collector, I don't know. But basically, here they are in the savanna of Eastern Africa about 1 to 2 million years ago. All right. Now, intelligent life appeared on Earth very late, okay, halfway through the life of our star. All right. Did life on Earth show anything that we would call intelligent, like Homo erectus? Okay. And this is the whole column of life again, showing you where Homo erectus appeared, okay, in the last million years of a column of 4,600 million years, okay? And if you were to expand just the last 500 million at the top, or the last 600 million at the top from the Cambrian explosion onwards, okay, you can see how recent the Homo erectus event is compared to the story of life on Earth. Okay, I mean, fish have been around, plants, amphibians, reptiles. Reptiles appeared in the Carboniferous. They still exist around us. Dinosaurs appeared sort of at the boundary of the Permian and Triassic and ruled the Earth for close to 200 million years, if not more. We've been latecomers here. Homo erectus is not even us, but it's our ancestor, evolution-wise, and it appeared about 1 million years ago, or 1 to 2 million years ago. Okay. So, what this tells us, what this tells me at least, is that intelligent life, because it appeared late on Earth and really serendipitously, the reason why Homo erectus appeared is because all of a sudden mammals, following the KPG impact that wiped out the dinosaurs, mammals, which were, burrowing rodents 66 million years ago, were all of a sudden free to roam and to evolve. And so there's an element of serendipity here. Dinosaurs that ruled the Earth with big brains for 200 million years never felt the need to evolve intelligence, meaning the ability to use tools and technology to transform their environment. Okay, mammals did, and for very specific reasons that are still being debated. But it had to do with the fact that there was climate change. The savanna became drier. They had to stand up to look at their environment, to look for prey from a greater distance. All kinds of ideas that I think are reasonably good, speculating about why we developed intelligence and tools. Being in a more open savanna, you had to reach your prey from a distance. This is what encouraged the use of tools, throwing rocks, arrows, rather than just trapping your prey by surprise. Intelligent life appeared late on Earth and serendipitously. It didn't have to. It's not, evolution is not directed. It's happenstance. You have mutations that take place, which may or may not favor your survival in your given environment. And if they do, then you survive, then you reproduce, and that trait gets reproduced or perpetuated. It's a very hit and miss approach that evolution uses. And nowhere is there written that at some point evolution shall evolve intelligence. It's one of those things where it happened on Earth because it created a very distinct advantage for a specific species at the time. Okay, so how do you quantify then what fraction of planets that have life on them where life actually becomes intelligent? Well, it's very difficult to do, and I am suggesting that we simply, to get a rough estimate, put the time for which we've had intelligent life on Earth, 1 million years, and against the age of the Earth, 4.6 billion years, with, it could be 4.6 or a little less, depending on whether you want to hit the very beginning of life on Earth or just the beginning of our planet's life. But roughly 1 million years, if you were to take the Earth sort of randomly through its history of 4.6 billion years, what would be your chances of finding intelligent life on it? Well, it's 1 million years out of 4.6 billion, okay, is what this number represents. And again, it's not a very good estimate of how you would evaluate the fraction evolving intelligence, but it's a way of doing it. And F sub I, therefore, you divide 1 million by 4.6 billion is 2 10,000ths is what that fraction F sub I is. Okay. 2 10,000ths. Now, it's not zero, but this is going to bring n down seriously. Okay. The reason why I think n is a small number, I can sort of spoiler alert, is because F sub I is such a low number. Okay. In other words, intelligent life is rare in spite of the fact that life itself could be very common. What fraction of intelligent life then becomes a civilization? Well, how do you define an advanced civilization? We can define it in different ways. You can choose the first radio telescope transmission, Jansky's work. I like to use Maxwell's equations. When James Clerk Maxwell came up with, these equations that are essentially a formulation of how electromagnetic energy propagates, we, for the first time, had a mathematical and physical understanding of electricity, magnetism, light, radio waves. That is, in my view, the root of technology today. And of course, of our ability to communicate with other planets through light and radio waves. And so that happened in 1865. So which coincides with the end of the Civil War, by the way. So I would say it's not a bad date to sort of pick arbitrarily. Before 1865, we were intelligent, but we were not an advanced civilization. Since 1865, we've been an advanced civilization. How about that for arbitrary? Okay, so evolution of intelligent life to an advanced civilizations on the scale of the geology or astronomy is a rapid thing. You go from intelligent life, this is Homo erectus, in this case, Sangiran 17 of Java, 1 million years ago, to James Clerk Maxwell in about 1 million years. All right, so it's a very rapid evolution. As soon as you get to the point where starting to modify your environment with technology, basically you become unstoppable is sort of the idea. And you are now on track to quickly become an advanced civilization. It's going to happen because it gives you such a competitive edge, essentially, to improve technology upon technology once you start having it, including to fight your peers, other humans. And so you notice that in 1 million years, beard grooming has not really evolved much, but our understanding of physics has. Now, there might be advanced civilizations that essentially are not achieved because even though you have intelligent life, there could be dead ends to it becoming an advanced civilization. Okay, orcas, for example, we know are intelligent beings. They are very social. They have a language. They have complex interactions, and yet they don't use tools. They play with balloons in parks, but they don't really use tools. They don't engineer things. They live in a world where they are somewhat isolated from the rest of the cosmos. They have no practical way of understanding the universe around them. And so this might be sort of the dead end fate of an intelligent species that appears on an ocean world where basically they don't have the physical means to really develop technology, and especially understanding electromagnetic waves, which don't propagate well in water. You could have another world that has constantly a very hazy atmosphere, and jungle worlds, just very hot with a thick atmosphere. And you would never see the night sky. You would never have that perspective of where you are. And, you might have a concept of a flat earth for a very long time, if not forever, before you realize that you're on a ball. So that could be also a dead end or a real dampener to an intelligent species advancing to an advanced civilization. You could also have a world where the gravity is high. It's so high that the rocket equation no longer works for common propellants that you can make, like hydrogen and oxygen. We are very lucky on Earth not just to have, combustible compounds that are common, hydrogen and oxygen, okay, but a gravity that's low enough that the rocket equation allows you to launch something into space. But imagine you were on a planet that has a gravity of same as the Earth, but gravity that's say twice or 3 times more. The rocket equation would no longer work. You would not be able to launch yourself into orbit with just chemical propulsion. And so there are different thresholds here depending on your assumption of the mass and the propellants that you use. But I always thought that this was interesting. Not every intelligent species will be allowed to have a space age or access to space. And so we are somewhat fortunate to be, on a world that is just low enough in mass that we can barely make it. But we know it's difficult. It's been slowing us down a lot. If we could get ourselves into space a lot more easily, if our gravity was 80% of what it is, everything else being equal, it would be very helpful. But you could also imagine a world that simply has a very thick atmosphere. I mean, Titan, for one, is much smaller than the Earth, yet has an atmosphere of 1.4 bars. You can imagine a world that has such a thick atmosphere that rocket propulsion would really be hampered. There you have it. Just too much friction all the way up to space. So there could be dead ends to an intelligent species becoming an advanced civilization, is sort of the idea. So I would say F sub C is not one. Not every intelligent species becomes an advanced civilization, but probably not close to 0 either, maybe 10%. Okay, so 10% I think is a reasonable number for F sub C. This is all somewhat arguable, but most intelligent species in our galaxy might not reach advanced civilization ever. I think it's sort of what this says. Finally, the longevity of a civilization. What's capital L? Well, on Earth, if you include the earliest big civilization, which was ancient Egypt, really, 3,000 years ago, well, 3000 BC onwards. This is the Nile Valley, by the way, with the Nile Delta up at the top and the Mediterranean above all this. This is really the cradle of us as a sort of a global civilization. And we've been around for only about 5,000 years. And, it's unclear, especially with what's going on right now in the Ukraine, it's unclear if we actually are bound, destined for, to becoming a million-year-old civilization. I don't know. Most civilizations on Earth have lasted anywhere from 500 to 5,000 years or so. I mean, just a few hundred years is sort of typical. And so I think that if you claim that L is a large number, much larger than L, than about 5,000, you are just being very optimistic. Okay, and that's okay, but you just have to recognize that nothing says out there that we are destined to being a million-year civilization. There are many things that could end a civilization. A large impact. This is Houghton Crater, where we do a lot of field work, 20 kilometers across. I put you the Eiffel Tower there for scale in the middle of the impact basin. It was formed by a bolide about 1 kilometer in size that came in at roughly 20 kilometers per second. We don't know the speed of it, but if it was 1 kilometer in size, the energy required was about 20 kilometers per second. So that's Houghton Crater up on Devon Island in the Arctic. Civilization might end because of overpopulation. These are 3 curves, 3 outcomes that are considered by the United Nations for the years to come. Either a continued exponential growth of millions of people, either we sort of start rounding things off with a yellow curve, or we actually start dropping the global population. So we're still somewhere between red and yellow here at the current stage. All right. Overpopulation could really lead to a collapse of our food chain and the death of millions, and of course, the demise of civilization in a big way. Pandemics I don't need to tell you that I did this little painting a while back of our recent experience with COVID, but pandemics could conceivably wipe out civilization if the virus, of course, is a lot more lethal than even what we've experienced so far. And then, of course, we could destroy ourselves with wars. And now that we have the means of global destruction, this becomes a possibility that wasn't true a few decades ago, well, half a century ago, but now is possible. Okay, so, and I must do a shout out here for Ukraine and all our friends over there who are really being unjustly invaded by the Russians right now. I think this is a real plight that has to be remedied. They have my full support. Civilization might be something that's very transient in the history of a planet. This is a painting I did showing sort of a geological column with past history, of course, at the bottom. And then all of a sudden, a civilization at the surface of our planet, which results ultimately in a layer of rust and concrete, and then further burial by marine sediments. And, we sort of become just a layer in geological time. Okay, so we tend to be caught up in our self-importance in the present, but geologically we really are occupying a very tiny, well, so far have occupied a very tiny window in our planet's history. So I would argue that historically cultures have lasted 500 to 5,000 years. We're now global, high tech, and can self-annihilate. Let's not be too pessimistic. Let's say that an average longevity for civilization is 10,000 years. That's double what we've had experienced so far. But I think that claiming that we're bound for 1 million is, I can't prove you wrong, but it's in my view really overly optimistic, and that would have to be recognized. Okay, so 10,000 I think has a historical basis to it, with a bit of optimism thrown in. Will last as long, at least as long, basically, as we've lasted so far. So where does this come to? I give you the numbers from this talk: 20 for R, 0.5 for F sub P, 1 for NE, 0.5 for fraction with life, 0.0002 for fraction with intelligence, 0.01, well, 0.1 for fraction with civilizations, and an average longevity for each civilization of about 10,000 years. What's N? N is 1, okay, which would imply that the nearest civilization to us would be, on average, 50,000 light years away, which incidentally is, of course, a lot longer than we've been radio communicating. We've been communicating by radio waves for a century, so we would be nowhere near being able to reach them with a radio signal if they were indeed 50,000 light years away. And also, if their average longevity is 10,000 years and they're located 50,000 light years away, if they had sent us a signal, then they would be dead by now if we received it. If we receive a signal from a civilization that lasted only 10,000 years, but it's located 50,000 light years away, then they're gone. Okay, so we still get the signal, but they're no longer there really sharing our galaxy. Okay, so there are some implications that come with the play of these numbers N and L in terms of the simultaneity of these civilizations and our ability to communicate with each other. So with N approximately equals to 1, we might be it. It could be it. It could be us, or there might be another one, or even a few others. I mean, we could be off by several, even a few orders of magnitude here. But the point is, I think this is sort of the hypothesis to beat, as opposed to assuming that somehow there are many out there. And because I think that it's a lot of optimism to think or to expect that there would be many out there. I think we should expect us to be unique in our particular galaxy, but still search, and then be happily surprised if we found others. And of course, that would be a great day. This is a way of re-expressing this Drake equation with the values that I'm suggesting, and the color coding that indicates the error bars, if you will, the uncertainty that accompanies each term. So numbers in white are off by sort of certain within 1 order of magnitude. Numbers in yellow are potentially off by 2 orders of magnitude. Numbers in orange are potentially off by 3 orders of magnitude. Numbers in red by 4. So there's certainly no certainty here. Nobody's claiming that n equals 1. We're just saying that with some arguments that are somewhat pragmatic and based on data that we have, with as little speculation as possible, n doesn't turn out to be a large number. N turns out to be a small number. And so what does this do for us? Well, it doesn't mean that we are here by divine intervention. I mean, even if we were unique in our galaxy, it would be the product of natural processes and chemistry followed by biology and evolution. So from that standpoint, our uniqueness would have nothing to do with our godliness. Okay, it would still be the fact that we are, we're simply rare as an outcome of natural processes. I think what this would do to us is reinforce our sense of responsibility for being really special, not necessarily important in our galaxy, but special. And in order to perpetuate ourselves, we shouldn't be waiting for rescue from other advanced civilizations in our galaxy, or somehow a day where we might join a galactic club. We might be really lonely for the long haul here and have a vast galaxy that's open to us to explore. The galaxy could still be teeming with other Earth-like planets, with microbes. Microbial worlds could be all over the place. Worlds with, things that are not super smart, like dinosaurs, could be common. Okay, ocean worlds with gigantic beasts, like orcas and whales and other. I mean, of course, we wouldn't expect those particular beasts. I'm just saying, giant marine animals. Okay. Could be common, but things with intelligence that are capable of using Maxwell's equations to design radio telescopes and fly rockets, that could be really exceedingly rare, and possibly of order 1 per galaxy at any given time. Okay. Now, the good news is we know of about 100 billion galaxies in our universe, so nobody's claiming we're alone in the universe. We might be in really good company in the universe. It's just that everybody's pretty far away. And, how do you go about a search for extraterrestrial intelligence like this? In my view, I think that we should, of course, do a search of nearby stars, just in the off chance we were off in a good direction by several orders of magnitude. We should do a search within our galaxy, especially the outer parts, because you don't want to be near the gamma ray burst zones. We should, of course, listen to the rest of our galaxy, but we should also pay attention, I think, to other galaxies, because if every galaxy has on average 1 civilization at any given time, you might be looking here at essentially a map of civilizations, and that could be really interesting. Maybe one of them happens to have beat the 10,000-year longevity thing. And be, sort of a super galactic lifetime civilization. Maybe some are emitting very loudly in, radio bands or with optical laser that are, technosignatures, just because of their characteristics. So I think that we should expand our search to extragalactic searches. And to that effect, one place that we might really look again, because we've looked at M31 Andromeda in the past, but only fleetingly, we should essentially have radio telescopes pointed at Andromeda at all times, just in case we are capturing something a little bit off natural from Andromeda. This is an image that I put together just to show how big Andromeda actually is in our night sky. I mean, we don't see it like that, of course, because, I mean, it subtends, I think, 6 degrees across the night sky versus about, might not be degrees, it might be minutes. Anyway, it's about 3 times larger in angular dimension than the moon is. But of course, it's 2 million times dimmer. And so that's why we don't see Andromeda so crisply in our night sky compared to the moon. But if it were bright enough, this is how big it would be. So Andromeda, I think, is a nearby galaxy that we should really listen to and monitor in the off chance that if it has one civilization at this time, and of course, now we're talking about our time, it would have existed, 2 million years ago. We might have a chance of detecting it by looking at this whole galaxy. This is a map, a histogram showing you the number of galaxies per million light years away from the Earth. So within our neighborhood, within 1 million light years, there's about 54 galaxies or galactic bodies. And then as you go farther out, all the way to 66 million light years, you have fewer and fewer galaxies. And then, so you can really see our local cluster here of galaxies, our local group of galaxies. And what's interesting here is that all these galaxies that are within 66 million light years from us, if they were somehow able to track what was going on Earth, would not have heard of the dinosaur KT extinction yet. Okay, they would have a view of the Earth that is that's really limited to sort of the near term. If you're beyond 66 million light years from us. So as an epilogue, I will just say this. Of course, we don't really know the value of n, but it's more likely small than large. Our galaxy might be teeming with life, just not lots of advanced civilizations. The Fermi Paradox, there might be no paradox at all. If n is a large number, where are they? Well, n might not be a large number, and so therefore there's no paradox. That's why we don't hear from anybody. Even if we're alone in our galaxy with over 100 billion galaxies in the known universe, we might still be very good company. SETI searches and monitoring should focus on extragalactic searches, specifically the nearest galaxies to us. And we should take good care of the Earth. No one will come save us. There's no galactic club to join, possibly. I will end with a couple of slides like this. This is a cartoon that I did to celebrate Frank Drake's 90th birthday last year. Frank Drake turns 90 in a galaxy far, far away, where some other alien civilization came up essentially with the Drake equation as well, because it's so fundamental in its structure and significance. So that evening, the workshop participants were treated to a presentation on the Eckhart equation by none other than Prof. Narf Eckhart itself. Narf Eckhart is Frank Drake spelled backwards. Anyway. So thank you, Frank Drake, for the Drake equation. And if you haven't had enough of me talking, I'm giving a talk with Tucker Hyatt of Wonderfest at as part of the Bay Area Science Festival on April 25th, so just 5 days from today, on Starship Reality Check, the science of deep space travel. So we're going to be talking about the plausibility of interstellar travel and what would have to happen to make that possible, if at all. Thank you for your attention.
Wonderful. Thank you very much. We'll take questions. If anyone has, you may type them into the chat, or if you'd like to unmute yourself and just ask with your voice, that's fine too. Liz writes, thank you very much for an interesting presentation and a glimpse at your wonderful artwork as well.
Thank you.
Pascal, I was wondering myself about, I readily think of that you need time for a radio signal to reach from one planet in a star system to another planet in a different star system, but then also you might also have if it passes by your planet and keeps going onward, and you miss that sort of window of when a civilization is broadcasting, that could be another problem. Is that correct thinking?
Yeah, if you're talking about a signal that is transmitted for the purpose of reaching, someone out there, the more repeated, the longer the signal, the better your chances. It's just like a radio call on Earth. You're trying to reach somebody, you want to make several calls, okay, in hopes of being heard. But we actually make constant radio noise through radio leakage, it's called. And the Earth has been transmitting powerfully in radio waves since the 1930s mostly, and it's actually ironic that some of the most powerful radio broadcasts from the 1930s were actually Hitler's speeches, and so those are on the forefront of what's essentially expanding as a sphere of radio transmission from the Earth into our galaxy.
Talk about deleting your old tweets.
Talk about deleting your old tweets. Yeah, exactly. But, joke aside, they would eventually, if they were listening long enough, see that, we've evolved away from that, although we still have problems of that nature today even. You could hear, so if you're within the sphere expansion of your radio leakage of a planet, you would hear that planet's broadcasts for quite a while. You might miss the first message, but eventually you would catch up.
Now, even if and when we stop communicating with ourselves by radio signals, we'll still be emitting presumably electromagnetic field radiation through just as a side effect of other activities that we're doing.
Yeah. So that's one thought. The other, of course, is that we might actually become really radio quiet if for some reason we had a complete shift of technology and went, I was joking with cable earlier. We all got cable. Okay, so if all of a sudden we use optical laser, to communicate. So optical laser is another means of communicating over interstellar distances. It's more prone to absorption by, smaller particles, dust in particular. But radio waves can see through dust quite well. But anyway, optical laser could be a way of really being, of showing a sign of intelligence here on this planet by beaming around an optical laser. So Jill Tarter at the SETI Institute gives a very good talk where she discusses different techno-signatures that we could be looking out for. So I think we should have our eyes peeled for all of those, but including more systematically extragalactic sources in my view.
Another idea that comes to my mind is quantum entanglement as an idea for possible future communication. Is that something that SETI is watching or listening for?
I know, yeah, it's part of the trade space, although I know very little about that myself. So I'll just.
Yeah, I think it's speculative at this moment. Philippe asks, what are the chances that a silicon-based life form as opposed to carbon-based might exist?
Yeah, so, silicon has the same electronic valence, if you will, the same number of electrons that are capable of chemical bonding as carbon. And so it's been often speculated in sci-fi stories in particular that instead of being carbon-based, you can imagine life being silicon-based because it would be essentially the same chemical products, so to speak, except that Si would replace C. But the problem is that the energies involved in these chemical bonds are very different. SiO2, which is what you find, which is silica, silica, which is what you find in silicate rocks, is a very strong bond, which is why rocks are so strong. Okay, whereas CO2, carbon dioxide, even in condensed form, is a very friable and easy to break apart chemical molecular bond. So the reason why life uses carbon-based chemistry is not just because it can, but because it's easy. It is easy energetically, it is efficient, it doesn't require a lot of energy to break or make. It offers a huge versatility in terms of the range of chemical products you can form quickly. Whereas silica-based chemistry, even though technically on paper the reaction looks like it's the same, the energies involved are so much greater that it is not something that you could imagine life favoring. You know, could it exist? It's hard to say no, but it's very unlikely. You know, we tend to be worried about how geocentric we are in our search for life. You know, we're looking for things that we are familiar with. You know, we only know one form of life. Shouldn't we be more open-minded and looking for other forms of life? But at another level, we're just being very pragmatic about what makes our life chemically so efficient and possible. And that's because it's carbon-based. Carbon being a very common substance in the universe, even more common than silicon. So I would say that the burden of proof for those who are advocating silica-based life is to actually show us how this could happen in a, you know, sort of controlled environment, maybe, or a lab. And I can't imagine that being a practical thing to do.
I see a hand up from Nick. Go ahead and.
Thank you. Excellent talk, Pascal. Really enjoyed it. I've actually sent you a couple questions, but I sent them to you, and I'm not the moderator, so I'll have to ask them. I'm happy with microbial life. And by my calculation, if you look for microbial life, the number doesn't improve a lot, it's 5. But would the equation change if you change the assumption of only looking for microbial life? Or can you simply just delete the right-hand factors?
I think you just delete the right-hand factors, because microbial life, I would think that N would be more than 5, though. But you would be looking at the first terms and going all the way to F sub L. And then you will not have the F sub I to bring everything.
Yeah, that's 20 times 5.5 times 0.5.
Yeah. And then, however, well, exactly. And then in terms of how long the microbial life could last, which is the L factor, you still have to factor that in. Okay. It wouldn't be the longevity of an advanced civilization now, it would be the longevity of microbial life. That we know on Earth has, going back to the point about robustness, that's been going on for 4.5 billion years. So that's where you would pump up N to a very large number.
Ah, okay.
Yeah.
Okay. Yeah. So I was wondering if I was missing something. Second, I'm not sure why you would advocate looking for life in another galaxy. If you have a fixed amount of money, why not spend it pouring it into looking at nearby stars? At least we have a chance of reaching somebody, or in some kind of time, maybe 100 light years would make more sense, wouldn't it?
You're right. It sort of depends on the question you're trying to answer. If you want to establish communication with another advanced civilization, then there's no point in looking beyond a few, tens of light years. And that is something that, we've done and we should do more of. And because it's important, if we could not just detect them, but communicate with them. But we're also saying, we're trying to answer the question, are we alone? Are there others? Now that question doesn't require us to be in contact with them. It just requires us to
find them,
hear them, to find them once, and of course, be sure about finding. In that sense, why not broaden your search to a patch of sky that has 100 billion stars concentrated in a very small area, okay? And just listening thoroughly to that. Of course, they're much farther. There'll be a lot more attenuation of radio waves. You're talking about signals that will be much weaker. But then if you're looking for a civilization that's somehow really advanced and capable of being very loud, either in optical laser or radio waves, you might get lucky. So all I'm saying is, if every one of these patch has at least one civilization, that's a galaxy, it's one civilization, then you ought to be focusing on those, as well as looking in your nearby neighborhood for communication. Detecting life in a different galaxy, of course, will no longer be about communication. If you found something out there that was being loud and broadcasting, it wouldn't tell you that, you wouldn't be able to communicate with them, but it would tell you that a civilization can become so big and loud, and therefore must have acquired, must have survived long enough to acquire very powerful and potent technology. That will give us hope, or at least some sense that we're not doomed. We're not doomed.
Thank you. We have another question from July asking, what sparked your interest in your current career choice?
Well, I think like anybody who's interested in astronomy, it's sort of the profoundness of the questions we are able to ask and sometimes try to answer. Many people go through life really worried about our day-to-day concerns and treat astronomers as people who are not well grounded, who have their head in the sky and are not practical people. But I think it's the complete opposite. When you are singularly focused on your day-to-day concerns and life on Earth, you're a bit like an ostrich who sort of keeps their head on the ground and then loses track of the big picture. The big picture is really important. That's exactly what's happening to us. And we're on this little ball that's careening at 30 kilometers per second around a star that itself is careening at 250 kilometers per second around the center of the galaxy. And this is a reality. And we are, being hit by cosmic debris, both now from our own solar system and interstellar debris as well. I don't know if you heard, but we've now, the U.S. Space Command has now confirmed that what two astronomers at Harvard had essentially interpreted was a bolide, a meteor that entered the Earth's atmosphere at interstellar speeds, hyperbolic speeds in 2014, was actually an interstellar object about 0.5 meter in size, and that's now confirmed. So this was before, in terms of when it happened, it was before Oumuamua's flyby of our system. So that is now the oldest record, the first record of an interstellar object, coming into our system.
And how fast was that moving?
I forget the number. I don't have it in my. I don't have it off the top of my head, and it depends on the referential that you're using. But I don't have it on top of my head.
Or I suppose how long did it take to pass out of our solar system?
Well, actually, that object entered the Earth's atmosphere and broke up.
I was thinking of Oumuamua.
Yeah. Oumuamua right now is around the orbit of Neptune. It's not quite there yet, but it's on its way.
That's pretty quick, though.
Yep.
July asks, what do you remember most about working with Carl Sagan?
Oh, Carl Sagan was a great guy. I mean, I think he was a great person. I didn't have a huge amount of interaction with him, but when I was his TA, I was the sole TA for that class that he taught. It was a class on science writing. It admitted 25 students, but 3,000 applied. 3,000 undergrads applied to attend Carl Sagan's science writing class, and 25 were picked. So I'd helped Carl screen the applications first. And then once the class started, I was his TA. We were grading essays from the 25 students once every 2 weeks. And Carl was very into it. He really cared about his students and what they were writing. And so I was in his living room every other Saturday afternoon grading these essays with him. And we were exchanging our comments about these essays and what we thought of them. It was delightful. And I remember in his living room, there was this replica of the Rosetta Stone. So if you remember, the Rosetta Stone is this giant slab of rock that has the same text written in 3 ancient languages, one of which is hieroglyphics. And when the Rosetta Stone was first found by soldiers of Napoleon, it enabled Champollion, a French linguist, to, for the first time, decipher Egyptian hieroglyphics, because he knew how to read the other 2 texts, which told the same story. And so we had essentially a translation of that text in hieroglyphics. Anyway, the Rosetta Stone was eventually taken out of Egypt by the French, but then taken by the British Navy when the French were defeated there in Egypt, and it ended up in the British Museum. Anyway, for Cosmos, Carl Sagan went back to Egypt to tell the story and created a replica of the Rosetta Stone. And when I admired his Rosetta Stone in his living room, he said, Pascal, you won't believe the trouble I had to get the Rosetta Stone out of Egypt the second time. Okay, because after the filming was done, he decided to keep it, of course, as a prop for his living room. And the Egyptian customs apparently were giving him a hard time to take that thing out of Egypt the second time, which I thought was funny.
We have a question. Philippe asks, is it reasonable to assume that the periodic table is universal and the distribution of elements found in our solar system is similar across the Milky Way, and therefore life forms would be reasonably close to ours?
Yes, that's the power of physics and chemistry, is what applies here applies elsewhere. I mean, obviously, in other words, the general laws apply. And if you have specific conditions, well, then, this or that type of chemistry will be favored. But the fundamentals of chemistry are not going to be changing, or the fundamentals of physics.
Right. The table's not an arbitrary construction necessarily.
Yeah, no.
A question from Dan. Do you have any thoughts as to potential dangers from extraterrestrial civilizations?
Well, no, precisely because no, I actually don't think that's a significant risk at all. Now, history might make me regret these words, but no, I don't think so at all. In fact, I think the greatest danger to us is ourselves. That, if anything, that's the message from all this. We are it, and we had better take care of ourselves and behave responsibly, and sort of be good stewards of the environment here on Earth and on other worlds we might visit. It's Earth-like planets are hard to come by, and advanced civilizations are even harder to come by.
And what do you base that on? I mean, that's good news, if it's true.
Well, I base it on what I just sort of mostly my talk tonight, where I think F sub I is an unlikely outcome, and therefore is a small number. Life might be common, but intelligent life took very specific circumstances on Earth to emerge, and it's not at all written that it will appear whenever life appears. It's not a necessary outcome of life intelligence, and because of that, it could be really much rarer than we think. Yeah. So again, we don't live in a Star Trekian or Star Warsian galaxy. I think we live in a place that's a lot more quiet and lonely and wild. I mean, there are planets with wild beasts, I'm sure, but national park stuff.
We have a question from Prasad. What if there is an advanced civilization in some other dimensions, or a multiverse anticipated by the Paul Dirac equation?
Yeah, so then they are in a separate universe, and then their interactions with our universe are essentially isolated from us. They are isolated from us, unless you speculate that there are ways to travel from one universe to another. But now you're talking about a civilization. If it were capable of doing that, that would be so far advanced compared to us. It goes back to, well, first of all, it's unclear to me that we've had enough time to come up with something like this. I mean, it took us about 5 billion years, okay, to emerge, for life to reach this point on Earth. It could have happened a little sooner, but not a lot sooner. Okay, so 5 billion years, give or take, is what it took for intelligent life to appear on Earth. The universe itself is only 13.8 billion years old. So it's not like, another civilization would have had, tens of billions of years to sort of reach some universal maturity. It's not a very long time if it took us so long to get to this point, just humans. So I don't know. I think it seems to be very hard for people to accept that we might be alone. And I'm okay with that. I cannot rule out other advanced civilizations being nearby or in a parallel universe. Of course, it's all conceivable, but I don't see it being likely.
Let's see. July asks, how would we decipher a message if we were sure that we received one? Is mathematics the universal language?
Yeah, so you'd be looking at something that, so there are different traits to technosignatures, okay? Repetition could be one, but then repetition of a pattern that does not seem natural, something that might seem coded, for example. Pulsars, for example, are, neutron stars that are beaming in specific directions, and when the beam sweeps the Earth, you get a pulse. So that's why they're called pulsars. Now, that pulsing is relatively regular, and quite predictable in the sense that you can sometimes measure a slowing down or speeding up, depending. But if you were dealing with an artificial signal, it would have more complexity to it, presumably, more than just a pulse. It might have something more, like something more akin to a coded message. This goes into the whole field of coding, in the sense of coding messages versus noise. And there are many ways in which you can make a signal reflect intelligence and intent versus a signal that's just random noise.
That makes me curious to ask, is there a can you give any glimpses to what the chain of command is if you detect a signal? Do you call the president right away, or do you call someone and then they call someone? And I'm also kind of wondering, like, if you received a signal, would you even tell the public? But I know you probably can't even answer that. So
we have there's a procedure in place. Yeah, if you receive a signal, first of all, it's unlikely to be clear that it's extraterrestrial immediately. So you're going to have to verify it. This whole verification process is unlikely, first of all, to be kept secret. If there was a signal that was being suspected as being a technosignature, of course, we wouldn't necessarily publish it or broadcast it, but it'd be very difficult to keep it hush-hush for a very long time. And meanwhile, you have to study it to make sure that it is a technosignature, not of the Earth. Because, of course, we are transmitting all kinds of signals from sources that we are known and unknown, in space and around space. And so we would have to be sure that what we're detecting is not of the Earth. That process itself is unlikely to keep that thing secret. Now, once we've established, at that moment where we establish, okay, this is definitely not from the Earth, this is alien, from an alien civilization, this is a technosignature from outer space. At that point, I know the SETI Institute would publish it, would announce it. It's not going to give a phone call to the president. I mean, we would expect a phone call from the president.
You don't have a devoted telephone line for the man or woman in the White House.
But we suspect that the president would, or powers that be, would have contacted the SETI Institute before any announcement is made. Yeah.
Philippe asks, do you frankly feel we are remotely ready to accept the evidence of other advanced life forms outside our solar system and accept the possibility of learning about them and possibly communicate with them?
Yeah, I mean, it all depends on what you mean by life forms. I think that, when we're talking about the James Webb Telescope, looking at exoplanets and analyzing the atmospheres of exoplanets, the ones that are nearby, of course, and being able to tell us whether or not they have life on them. Oxygen being an example of something that would probably indicate life. I mean, most likely. Why? Because oxygen is very reactive. Oxygen, if it was just sitting in an atmosphere without life being involved, would just react with the rocks, turn into, you'd end up with Mars, an oxidized surface with not a lot of things metabolizing the oxygen. If oxygen is in the atmosphere, that means something is replenishing it for it to be there. That something has to be life, because oxygen is not something that is given out by volcanoes or normal geology or anything like that. So an oxygen-rich atmosphere would tell you that there is life on a planet, and not only that, but abundant life to the point of modifying its atmosphere to show the presence of oxygen. Mars could have life in the underground, but it hasn't been abundant enough to turn the atmosphere into an oxygen-rich atmosphere. And that's okay, that's possible. But if it's there in abundance, like it is on Earth, then you're going to have an oxygen signature or something that's really out of equilibrium, for non-biological reactions to sort of, that would indicate the fact that that's involving life. Now, I think the community is ready to accept that. That's what we're looking for. We're looking for alien life. Of course, we won't know for a very long time what type of life we found. Is it microbes? Is it forests? Is it, is it herds of stuff? We don't know. We're not going to know for a long time. But I think detecting something that, an oxygen-rich atmosphere within the systems of the nearest stars would be really a big deal. Like if Proxima Centauri Bravo had a oxygen-rich atmosphere, that would be an incredible find. That would be an incredible. I think that's a mission to Proxima Centauri Bravo immediately. Like we would gear up for that.
Well, I seem to recall there was evidence in the atmosphere of Venus just recently discovered of possible.
Yeah, that's the discovery of phosphine. Again, that's an example of a chemical that is associated with life, is synthesized and released by life, but can it be created by natural processes that are not biological? Yes. So right there, that makes the discovery of phosphine all of a sudden less significant than we thought. Mm-hmm. Well, than the people who published it thought. So we're going to expect some hit and misses like this along the way. We'll get very excited about something that could be due to life, but turns out in all likelihood not to be due to life. I think my talk this evening was just to lower the expectations a bit. SETI is a worthy pursuit, and I think it needs to be funded and supported. Nearby stars, our own galaxy, and other galaxies. But at the same time, our expectations should be low, because I think we're unlikely to be many.
Well, we also have many words of thanks and praise in the chat. Fantastic work, super presentation. Thank you. We'll look to see you on April 25 for your next talk. So thank you everyone for these great questions.
Thank you, everybody. Thank you.
Thank Linda, you. Yeah. Yes. Can you hear me?
Yeah, I hear you. I was just going to invite you to say a last word.
Oh, thank you so much. And I'm so pleased that it's been recorded, because it's something that people are going to want to take a look at again and listen to again. And thank you for showing us your artwork embedded in this wonderful talk. Oh, yeah, I wish so many more people got to hear this tonight.
Thank you, Linda.
And thank you. I look forward to seeing you again.
Thank you, Jay. Thank you, Linda. You guys are awesome. And I hope you have enough support at the San Francisco Amateur Astronomers. I think you're a good society, and I know you do a lot of outreach, which is great. Thank you.
We had our 70th anniversary this January.
Wow.
70th.
Awesome.
Yeah.
Well, thanks again. Thanks so much.
Thank you.
Thank you.
Thank you, everyone, for coming.
Good night.
Okay, good night.